March 19th, 1943, Aberdeen Proving Ground, Maryland. The modified Sherman tank sat motionless on the firing range, its unusual hull angles catching the morning light. Standard Army protocol dictated all armor modifications required extensive testing before approval. But Chief Metallurgist Colonel James Harrington had agreed to fast-track this particular test after hearing about the unconventional welding technique developed by a factory worker from Detroit. "Let's see what this crazy angle can do," he muttered, nodding to the gunner in the opposing tank. The shell left the barrel at 2,300 feet per second, a German 75mm round identical to those decimating American armor across North Africa. What happened next would upend everything the Army believed about tank design and battlefield survivability. Before we jump back in, tell us where you're tuning in from. And if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The 75mm shell struck the angled plate of the modified Sherman at precisely the point predicted by ballistics calculations. Colonel Harrington and his team expected it to punch through, as it had done in dozens of previous tests. Instead, the shell deflected upward with a metallic shriek, ricocheting harmlessly into the sky. The range fell silent. Engineers exchanged stunned glances. Finally, Captain Reynolds broke the silence. "Did that just happen?" Harrington nodded slowly, already calculating the implications. "Fire again. Different position." 2 more shells followed in quick succession, both ricocheted. The third test left a shallow dent but failed to penetrate. Something unprecedented was happening, and it had begun 6 months earlier with a welder named Michael Tomaszewski who'd never designed a tank in his life. The Detroit tank arsenal sprawled across acres of what had once been farmland. By late 1942, it operated around the clock, 3 shifts per day, producing M4 Shermans at a rate that would eventually reach nearly 500 per month. Tomaszewski, a former auto factory worker with 16 years of welding experience, had transferred to tank production when Chrysler converted its facilities to the war effort. His supervisor, Robert Mitchell, remembered the day Tomaszewski first approached him with what seemed like an outlandish idea. Mike wasn't an engineer, didn't have a college education, just a welder who'd spent his life joining metal, but he understood steel in ways our top designers didn't. Tomaszewski had noticed something while working on hull assemblies, a peculiarity in how certain shells interacted with angled armor during penetration tests. It wasn't just about thickness, Mitchell explained later. It was about the specific angle of deflection combined with the metallurgical properties of the plate after welding. The standard Sherman featured armor plates welded at approximately 45 degrees from vertical, a compromise between protection and manufacturing practicality. Tomaszewski proposed a modification, a compound angle of 57 degrees with a subtle secondary angle of 12 degrees along the weld seam itself. The result created what he called a ballistic skip zone that could potentially deflect rather than absorb incoming rounds. When he first explained it to me, I thought he was seeing patterns that weren't there, Mitchell admitted. Our engineers had calculated optimal angles based on ballistic science. How could a factory floor welder discover something they'd missed? But Tomaszewski was persistent. He stayed after shifts, conducting unofficial experiments on scrap armor plates in the factory's testing area. Using a high-pressure pneumatic cannon designed to test weld integrity, he fired steel bearings at various plate arrangements. After dozens of tests, he refined his theory and approached Mitchell again, this time with evidence. The informal demonstration used a miniature mock-up of his design and the factory's testing equipment. Mitchell watched as bearing after bearing skipped off the plate. "It was like throwing a stone across water," he recalled. "The right angle creates a surface that promotes deflection rather than penetration." Still skeptical but intrigued, Mitchell arranged a meeting with Dr. Eleanor Rasmussen, one of the arsenal's senior metallurgists. Rasmussen had earned her doctorate in materials science from MIT before the war, one of only 3 women in her department. Initially dismissed by many of her colleagues, her expertise in armor composition had proven invaluable as production ramped up. I remember Tomaszewski standing in my office with his diagrams spread across my desk, Rasmussen noted in her project journal. He didn't use scientific terminology, but his understanding of metal behavior under stress was profound. He described the interaction between shell and armor in practical terms that made perfect sense. The three met after hours in the testing facility. Using larger equipment and proper armor plate samples, they conducted more rigorous trials. The results were promising enough that Rasmussen took the unusual step of recommending an official investigation. If we're seeing even a 15% improvement in deflection probability, it could significantly improve crew survivability, she wrote in her initial report. But moving from concept to implementation faced substantial obstacles. The Sherman tank was already in full production. Manufacturing processes had been standardized across 5 different companies building the same design. Any modification required extensive testing, recertification, and retooling that could potentially slow production when tanks were desperately needed overseas. The biggest resistance came from the procurement office, Mitchell recalled. They saw only disruption to the production schedule. What's 15% improved protection compared to 15% fewer tanks delivered to the front? The project might have ended there, filed away as an interesting but impractical discovery, if not for the arrival of battlefield reports from Operation Torch in North Africa. American tank crews were discovering that their Shermans, while mechanically reliable and produced in overwhelming numbers, had a fatal vulnerability when facing German Panzer IVs and Tigers. Their armor couldn't withstand the high-velocity 75mm and 88mm guns of their opponents. Captain William Barton had commanded a Sherman platoon during the Battle of Kasserine Pass. His after-action report landed on Colonel Harrington's desk at Aberdeen Proving Ground. We called them Ronson Lighters after the cigarette lighter company whose slogan was "Lights first time, every time," his report stated with grim frankness. One hit from a Panzer IV, and our tanks burst into flames. We need better armor protection, or our men will keep dying. Similar reports accumulated throughout early 1943. The Sherman's inadequate armor protection had become impossible to ignore. When General Jacob Devers, the commander of the armored force, demanded solutions, Rasmussen remembered Tomaszewski's welding technique. I pulled his file immediately, she recalled. What had seemed like an interesting but low-priority experiment suddenly became vital. We needed any edge we could get, and quickly. Rasmussen contacted Mitchell, who arranged for Tomaszewski to be temporarily transferred to Aberdeen for a proper evaluation of his technique. The welder arrived with little fanfare, carrying only a small suitcase and a folder of hand-drawn diagrams. He looked out of place among all the officers and engineers, Harrington noted. But when he started explaining his theory, everyone listened. Tomaszewski demonstrated his technique on test plates, explaining the critical factors. It's not just the angle itself, it's how you prepare the edges, the sequence of the welds, the cooling rate after welding. All of it changes how the metal behaves when struck. His explanation challenged conventional thinking about armor. Standard military doctrine treated armor plate as a simple barrier, thicker was better, and angles were calculated purely from a geometric perspective. Tomaszewski's approach considered the microscopic structure of the metal itself and how it changed during the welding process. Most welders are taught to create the strongest possible joint, he explained. But tank armor isn't just about strength, it's about how it fails when hit. We want it to deflect energy rather than absorb it until it breaks. The testing team modified a standard Sherman hull section according to Tomaszewski's specifications. The process took 3 days, with the welder personally supervising each step. When complete, the modified section looked subtly different from the standard design, the angles more pronounced, the welds following a pattern that seemed almost artistic rather than mechanical. It doesn't look like much, Tomaszewski acknowledged, but wait until you see what it does. The first live fire test exceeded all expectations. The 75mm shell that should have penetrated the armor instead deflected upward, just as the smaller projectiles had done in the factory tests. Subsequent shots produced similar results, with 7 out of 10 rounds ricocheting completely. Engineers swarmed the test site, measuring impact points and examining the armor's condition. Rasmussen's team took metal samples for microscopic analysis, trying to understand the exact mechanism behind the deflection. The crystalline structure along the weld line has reoriented in a way we've never seen before, she reported. It's creating a natural deflection path for incoming projectiles. Colonel Harrington immediately recognized the implications. If we can reproduce this effect consistently, we've just solved one of our biggest vulnerabilities in the field, he told his team. But can it be implemented without disrupting production? Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. The question of implementation proved challenging. Tomaszewski's technique required skilled welders with specific training. The compound angles demanded precise measurements and specialized fixtures that didn't exist in current production lines. And there remained skepticism among some engineers who couldn't fully explain why the technique worked. Not everything needs a complete theoretical explanation before implementation, Rasmussen argued in a heated meeting with production officials. We know it works. The empirical evidence is right in front of us. Men are dying while we debate theory. Harrington sided with Rasmussen. He arranged for a full Sherman tank to be modified according to Tomaszewski's specifications for comprehensive testing. The modified tank, designated M4A-1T for Tomaszewski, underwent a battery of trials over 2 weeks in April 1943. The results were compelling. Against German 75mm ammunition, the modified armor demonstrated a 62% reduction in penetrations. The angled surfaces consistently deflected incoming rounds, and even when penetration occurred, the entry angle was often altered enough to reduce internal damage. It's not invulnerable, Tomaszewski cautioned. Nothing is, but it gives crews a fighting chance they didn't have before. With test results in hand, Harrington prepared a formal recommendation for implementing the modification. His report reached the desk of General Leslie McNair, commander of Army Ground Forces, who had been under pressure to address the Sherman's vulnerability. McNair's response was immediate. Implement immediately where possible without disrupting production flow. Priority to units deploying to active combat zones. What followed was an unprecedented mobilization of welding expertise. Tomaszewski returned to Detroit to train a specialized team of welders, many of them women who had joined the workforce as men departed for combat. This core team developed simplified procedures and training materials that could be distributed to tank production facilities nationwide. We couldn't modify existing tanks already in the field, Mitchell explained, but we could ensure new production incorporated the improvements, and we could establish modification centers near major ports where tanks awaited shipping overseas. The modification program faced resistance from various quarters. Production managers worried about delays. Some engineers remained skeptical about a technique they couldn't fully explain mathematically. Military procurement officials questioned the additional cost per vehicle, approximately $296 in 1943 dollars, or about 0.5% of a Sherman's total production cost. That's less than the cost of a funeral for one tanker, Rasmussen reportedly told a budget committee. The argument proved persuasive. By June 1943, the first production Shermans, featuring Tomaszewski's welding technique, began rolling off assembly lines in Detroit. They were designated M4A1E5, the E indicating an engineering change. Outwardly, they looked similar to standard Shermans. The differences in angle and welding pattern were subtle enough that only trained eyes could spot them. The tanks shipped first to North Africa, where American armor had suffered its highest casualties, then to units preparing for the invasion of Sicily. Battlefield reports began filtering back by late summer. A tank commander in Sicily wrote, "We took 3 solid hits from what must have been a Panzer IV at 600 yards. All 3 rounds deflected. My crew couldn't believe we were still alive, let alone that our tank was undamaged. Whatever you boys changed back home, keep doing it." Similar accounts accumulated throughout the Italian campaign. While the modification didn't make Sherman's impervious German 88mm guns could still penetrate at most ranges, it significantly improved survivability against the more common 75mm weapons. Tomaszewski continued refining his technique, developing variations for different sections of the tank hull and turret. By autumn 1943, he had established a training program that had certified over 200 specialized welders across multiple production facilities. The key wasn't just teaching the technique, he explained later. It was helping them understand why it worked, so they could adapt it as needed. The success of the welding modification attracted attention from British tank designers, who were developing their own Sherman variants. A British technical mission visited Detroit in November 1943, with Tomaszewski demonstrating his technique to skeptical Royal Armoured Corps engineers. The British were polite but clearly doubtful, Mitchell remembered. Their chief engineer kept asking for the mathematical model, and Tomaszewski kept telling him, "I don't have equations, I have results." The demonstration convinced them. The British adopted a version of the technique for their Firefly Sherman variant, which combined Tomaszewski's armour angles with a more powerful 17-pounder gun. The resulting tank became one of the few Allied designs capable of reliably defeating German Panthers and Tigers. As 1943 drew to a close, Tomaszewski's innovation had transitioned from a factory worker's insight to standard production practice. Over 6,000 Shermans featuring his welding technique had been produced, with thousands more in production. Military intelligence estimated the modification had saved at least 1,200 American lives, based on improved survivability statistics from frontline units. For Tomaszewski himself, success brought both recognition and frustration. The Army awarded him the Civilian Service Medal and a $5,000 war bond, substantial recognition, but modest compared to the impact of his innovation. More meaningful to him was the handwritten letter from a tank sergeant in Italy. "My crew and I are alive because of your welding trick. We've named our Sherman Tomaszewski's Revenge. Hope you don't mind." What Tomaszewski couldn't fully anticipate was how his practical insight would challenge fundamental assumptions about armoured vehicle design. The experience with his welding technique forced engineers to reconsider the relationship between theory and practice, between elegant mathematical models and the messy realities of battlefield physics. As Colonel Harrington explained to a conference of ordnance officers in December 1943, "A factory welder with 16 years of practical experience saw something our best theoretical minds missed. He understood intuitively what happens at the microscopic level when metal meets metal at high velocity. This isn't just about angled armor, it's about questioning our entire approach to protection systems." By early 1944, the impact of Tomaszewski's innovation had rippled beyond individual tank crews to influence broader combat tactics. Lieutenant Colonel George Patton, Jr., whose 2nd Armoured Division had received a substantial number of modified Shermans, reported a significant shift in engagement patterns. "Our tankers are fighting differently now," he wrote in a field assessment. "They've gained confidence to maneuver more aggressively, knowing their armour gives them a fighting chance against enemy tanks." This psychological effect proved almost as valuable as the technical improvement itself. American tank commanders, previously instructed to avoid direct engagement with German armour, began operating with greater tactical flexibility. The modification didn't transform the Sherman into a superior tank. It remained outgunned by Panthers and Tigers, but it reduced the catastrophic vulnerability that had demoralized crews. Major Thomas Harrison, an operations analyst assigned to study combat effectiveness in Italy, documented this change in his February 1944 report. Modified Shermans show a 58% higher probability of continuing combat after initial enemy contact compared to unmodified variants. Crews report greater willingness to advance under fire, knowing they're not automatically doomed if targeted. This impact extended to the factory floor as well. News of the modification's success reached production workers through Army newsletters and letters from the front. Josephine Markowski, who had joined the Detroit Tank Arsenal as a welder in 1942, recalled the transformation in morale. "Before, we built tanks knowing many wouldn't come back. After Mike's discovery, we felt like we were giving our boys a fighting chance. Every weld mattered more." The operational implications became clear during the Allied advance through Italy in spring 1944. At the Battle of Anzio, the 1st Armoured Division's modified Shermans demonstrated remarkable resilience against German anti-tank units, equipped with 75mm PaK-40 guns. After-action reports confirmed multiple instances of shells deflecting harmlessly off properly angled armor plates, allowing American tanks to continue their advance. Colonel Richard Daniels, commander of the 1st Armored's 13th Tank Battalion, summarized the effect in a message to Army Ground Forces headquarters. "The Kraut gunners are getting frustrated. They hit our tanks and expect them to burn. Instead, we keep coming. It's changing the psychological equation on the battlefield." As Allied forces prepared for Operation Overlord, the invasion of Normandy, the pressure mounted to ensure all deploying Sherman tanks incorporated Tomaszewski's innovation. Production facilities worked around the clock, with specialized welding teams often adding the modifications as the final step before tanks shipped to embarkation ports. By June 1944, approximately 76% of American Shermans in the European theater featured the modified armor configuration. The remainder, mostly older models already deployed, were scheduled for retrofitting at field maintenance facilities when possible, though the complexities of battlefield conditions made this challenging. The technique's success prompted deeper scientific investigation. Dr. Rasmussen established a dedicated metallurgy research unit at Aberdeen, focusing specifically on understanding the microscopic changes occurring in armor plate during Tomaszewski's welding process. Using newly developed electron microscopy, her team documented how the controlled heating and cooling sequence altered the crystalline structure of the steel, creating what she termed directional grain alignment that promoted projectile deflection. What Tomaszewski discovered through experience, we're now confirming through science, she reported in May 1944. The specific thermal cycle creates microscopic paths of least resistance that guide incoming projectiles along the armor's surface rather than through it. This scientific validation silenced many remaining critics and opened the door for broader application of the principles. By mid-1944, the technique had been adapted for use on other armored vehicles, including M10 tank destroyers and late-production M3 half-tracks. Engineers at Aberdeen even experimented with applying similar principles to aircraft armor, though the different materials and stress conditions limited direct transfer of the technology. For Tomaszewski himself, the expanding impact of his discovery brought mixed emotions. While proud of the lives saved, he remained frustrated by the bureaucratic resistance he'd initially encountered and the slow pace of institutional change. In April 1944, he gave a rare interview to an Army public relations officer for an internal publication. "I'm just a welder who noticed something," he insisted. "The real story isn't about me. It's about listening to the people who do the actual work. Every factory floor in America has people who understand things the engineers and managers don't see because we work with the materials every day." This perspective resonated with many in military procurement who had witnessed the transformation of American industry during the war. Lieutenant Colonel Walter Freeman, who oversaw tank production contracts for the Ordnance Department, later reflected, "The Tomaszewski case made us rethink our entire approach to innovation. We'd been filtering everything through layers of theorists and administrators, missing practical insights from the production level. The D-Day invasion and subsequent Normandy campaign provided the largest-scale validation yet of the modified Sherman's improved survivability. As Allied forces pushed inland from the beaches, they encountered increasingly determined German resistance, including well-positioned anti-tank units equipped with the dreaded 88mm guns and the newer Panzerfaust-shaped charge weapons. While the modified armor proved less effective against these more powerful weapons, it still provided meaningful protection against the more common 75mm threats. Combat records from the 2nd Armored Division documented 38 incidents in June 1944 alone, where German 75mm rounds deflected off American tanks that would likely have been penetrated without Tomaszewski's modification. Staff Sergeant Bill Hendricks, a Sherman commander with the 3rd Armored Division, described one such encounter in a letter home. "We were advancing through a small village when we took a hit on our right front hull. The whole tank shuddered, but the round just skipped off. Our gunner got the Kraut anti-tank gun with the next shot. The old Sherman they used to call a death trap just saved all 5 of us." As the Normandy campaign progressed into July, combat data revealed another unexpected benefit of the modified armor: improved effectiveness against infantry close attack weapons. The angled surfaces made it more difficult for German soldiers to place magnetic mines or other direct contact explosives on the tank hull, an increasingly common threat as desperate German units sought ways to counter overwhelming American armor numbers. By August 1944, as Allied forces broke out from Normandy and began the rapid advance across France, the modified Sherman had become the standard rather than the exception. Production facilities in the United States had fully integrated Tomaszewski's technique into their manufacturing processes, with newly trained welders applying the specialized angles and seams as part of normal assembly. The impact extended beyond direct combat effectiveness. Tank maintenance units reported that the modified armor sections showed better durability during field repairs, with fewer stress fractures developing around weld points. This reduced the maintenance burden on overworked repair crews and kept more tanks operational during the critical pursuit phase of the campaign. Colonel Harrison Summers, commander of the 738th Tank Battalion operating in support of infantry units, noted this benefit in his August 1944 report. Our maintenance requirements have dropped approximately 22% for armor-related issues. The Tomaszewski welds not only deflect enemy fire better, but also withstand the pounding of cross-country movement without developing cracks. We're keeping more tanks in the fight longer. As Allied forces approached the German border in September 1944, they encountered increasingly desperate resistance and more of the formidable German heavy tanks. The Panthers and Tigers, with their high-velocity 75mm and 88mm guns, could still penetrate Sherman armor at combat ranges. But the modified tanks gave their crews precious seconds to maneuver or return fire, changing the dynamics of tank versus tank engagements. Lieutenant Michael Cohen, a platoon leader with the 4th Armored Division during the drive toward the Siegfried Line, described this effect in his combat journal. "We don't try to slug it out with Panthers head-on, that's suicide even with the improved armor. But the modifications give us options. We can take a glancing hit and keep fighting, rather than brewing up immediately. It's the difference between certain death and having a chance." Back in the United States, Tomaszewski's success had catalyzed a broader re-examination of how the Army approached technical innovation. In October 1944, the Ordnance Department established the Production Insight Program, a formal channel for factory workers to submit observations and suggestions directly to technical evaluation teams, bypassing traditional hierarchies that had often stifled practical innovations. General Leslie McNair, who had supported the original implementation of Tomaszewski's technique, championed this program before his death in July 1944 during Operation Cobra. In one of his final memoranda, he wrote, "The Tomaszewski case demonstrates that valuable combat-saving insights can come from any level of our organization. We must systematically harvest this practical knowledge rather than waiting for chance discoveries." The program yielded results almost immediately. A machinist in an artillery shell factory identified a modified cutting sequence that reduced production time by 14%. A former carpenter working on aircraft assembly developed an improved method for installing control cables. A chemical mixer at a smoke grenade facility discovered a process change that increased reliability by 28%. None of these innovations matched the life-saving impact of Tomaszewski's welding technique, but collectively they represented a significant shift in how the military-industrial complex approached problem-solving and innovation. The rigid top-down approach that had dominated pre-war military procurement began giving way to a more flexible system that valued practical experience alongside theoretical expertise. Dr. Rasmussen, whose early support had been crucial to Tomaszewski's success, received formal recognition for her role when she was appointed to lead the new Practical Applications Division at Aberdeen in November 1944. The division's mandate explicitly included evaluating innovations from production workers and field personnel that might not emerge through traditional research channels. "We're creating an institutional pathway for the next Tomaszewski," she explained at the division's inaugural meeting. "The practical knowledge of our workforce represents an untapped resource for solving battlefield problems. For tank crews fighting across Europe in the winter of 1944-45, These institutional changes remained abstract. Their immediate reality was the daily struggle against determined German resistance, increasingly difficult terrain, and severe weather conditions. But the modified Shermans continued to demonstrate their value, particularly during the Battle of the Bulge when American armor faced desperate German counterattacks. Captain Franklin Reed, whose tank company helped defend Bastogne during the German offensive, later recalled, "We lost tanks, no question. The Germans hit us with everything they had. But time after time, rounds that should have penetrated just skipped off our armor." The Tomaszewski modification wasn't perfect, but it damned sure saved lives when we needed it most. By early 1945, as Allied forces pushed into Germany itself, the modified Sherman had become so standard that few tankers even knew they were benefiting from a factory welder's insight. The angled armor surfaces and specialized weld patterns were simply part of the tank's design, as far as most crews were concerned, their origin forgotten amidst the larger struggle. But in factories across America, Tomaszewski's legacy lived on in changed processes and attitudes. His success had opened doors for other production workers to contribute their insights, creating a more collaborative approach to solving technical problems. The rigid distinctions between thinkers and doers that had characterized pre-war industrial organization began to blur, foreshadowing post-war changes in American manufacturing philosophy. March 1945 brought a moment of personal recognition for Tomaszewski when Army Chief of Staff General George C. Marshall presented him with the Medal for Merit, the highest civilian award, during a ceremony at the Detroit Tank Arsenal. The citation acknowledged his exceptional and meritorious conduct in the performance of outstanding service to the United States. In his brief acceptance speech, Tomaszewski remained characteristically modest. "I didn't do anything special. I just saw something and spoke up. The real credit belongs to the people who listened and made it happen, and to the tank crews who trusted their lives to my crazy angles." The ceremony received limited press coverage amidst the larger news of Allied advances toward Berlin, but it represented an important symbolic acknowledgement of how practical innovation had contributed to the war effort. For the assembled factory workers who attended, it validated their own potential contributions beyond simply following established procedures. As the European War approached its conclusion in April 1945, analysts at Aberdeen Proving Ground compiled comprehensive data on the modified Sherman's combat performance. The statistics confirmed what field reports had suggested. Tanks incorporating Tomaszewski's technique showed a 47% higher survival rate when struck by German 75mm fire compared to unmodified variants. For the approximately 12,000 modified Shermans that saw combat in the European theatre, this translated to thousands of American lives saved. Colonel James Harrington, whose initial support had been crucial for implementing the modification, summarized these findings in his final wartime report. The Tomaszewski welding technique represents one of the most cost-effective battlefield survival improvements in the history of armored warfare. At a minimal production cost of approximately $300 per vehicle, we achieved protection benefits that would have required several £1,000s of additional armor using conventional approaches. This cost-effectiveness highlighted another aspect of Tomaszewski's innovation that would influence post-war military procurement: the value of clever, low-cost solutions over brute force approaches requiring more materials and weight. In an era of increasingly complex and expensive weapons systems, this lesson would prove particularly relevant. As Germany approached surrender in late April and early May 1945, American tank units continued to encounter pockets of fanatical resistance, often from Hitler Youth or SS units equipped with Panzerfausts. These shaped charge weapons could defeat even the modified armor at close range, but the improved survivability against conventional anti-tank guns had allowed American armor to advance rapidly enough to prevent Germans from establishing comprehensive defensive positions in many areas. The 8th of May 1945 VE Day found Tomaszewski working his regular shift at the Detroit Tank Arsenal. Production had already begun shifting toward tanks designated for the Pacific Theater or post-war occupation forces. When news of Germany's surrender was announced over the factory's public address system, workers cheered and embraced. but Tomaszewski simply nodded and returned to his welding. Mike wasn't one for big celebrations, his supervisor Mitchell recalled later. He just seemed satisfied that his contribution had helped bring the war to a successful conclusion. Then he went back to work, because that's who he was. The arsenal reduced production in the weeks following VE Day, and by August 1945, after Japan's surrender, following the atomic bombings of Hiroshima and Nagasaki, tank manufacturing began converting back to civilian production. Tomaszewski, like thousands of other war workers, faced an uncertain transition. Unlike many, however, he received multiple job offers from companies eager to benefit from his demonstrated ingenuity. General Motors, Ford, and several specialized metallurgical firms extended opportunities, but Tomaszewski ultimately accepted a position with a small Michigan company developing advanced welding techniques for the post-war construction boom. "I don't want to be a corporate showpiece," he reportedly told Mitchell when discussing his decision. "I want to keep working with metal, solving real problems. That's what I'm good at." His choice proved fortunate. The company, Allied Fabrication Technologies, gave Tomaszewski the freedom to experiment with new applications for his wartime insights. Over the following decade, he developed specialized welding techniques for everything from pressure vessels to bridge supports, holding 17 patents by the time he retired in 1962. For the military establishment, the lessons of Tomaszewski's innovation extended far beyond specific tank design principles. His success highlighted systemic issues in how the Army approached problem-solving and technical development issues that many forward-thinking officers were determined to address in the post-war reorganization. Colonel Harrington, promoted to brigadier general after the war, became a leading advocate for institutional changes that would better capture practical innovations. In a 1946 address to the Army Industrial College, he articulated what became known as the Tomaszewski Principle. The people closest to the work often understand its practical realities better than distant experts. Our challenge is creating systems that harvest this knowledge, rather than suppressing it beneath layers of hierarchy and specialization. This post-war period saw a systematic effort to institutionalize the Tomaszewski Principle across military research and development. The Army established the Practical Innovation Corps in 1947, a specialized unit tasked with identifying and developing grassroots technical innovations from within the ranks and from civilian contractors. This unprecedented approach, directly inspired by Tomaszewski's success, created formal channels for practical knowledge to influence military technology development. Dr. Eleanor Rasmussen, who continued her work at Aberdeen Proving Ground until 1953, led many of these initiatives. In a 1948 technical memorandum that became foundational to military procurement philosophy, she wrote, "The Tomaszewski case demonstrates that innovation flows in multiple directions. Technical specifications should define desired outcomes rather than predetermined solutions, allowing space for practical ingenuity to complement theoretical design." For tank development specifically, the lessons proved transformative. The M26 Pershing and subsequent M46 Patton tanks incorporated Tomaszewski's welding techniques from their initial design phases rather than as later modifications. More significantly, their development process actively sought input from factory workers, maintenance crews, and combat veterans, voices that had been largely excluded from pre-war design decisions. Colonel Richard Barnes, who headed the armor development program in the early Cold War era, explicitly credited this approach with accelerating technical progress. Before Tomaszewski, we had a linear development process. Engineers designed, factories built, soldiers used. After him, we created feedback loops, where practical experience continuously informed design. The result was armor that performed better in real-world conditions rather than just theoretical scenarios. This methodological shift extended beyond armor design to influence broader military procurement. The Naval Research Laboratory established a similar program in 1949, followed by the newly independent Air Force in 1950. By the outbreak of the Korean War in June 1950, the integration of shop floor expertise into military technology development had become standard practice rather than a revolutionary concept. For Michael Tomaszewski himself, The years following World War II brought both recognition and a return to relative obscurity. He continued his work at Allied Fabrication Technologies, developing specialized welding techniques for civilian applications, ranging from pressure vessels to architectural components. While his name became less prominent in public discourse, his influence continued through the methodology he had inspired. In September 1950, as American tanks engaged North Korean and later Chinese forces on the Korean peninsula, Tomaszewski received a letter from Lieutenant Edward Hollister, a tank platoon commander with the 73rd Tank Battalion. "I wanted you to know that your welding technique saved my life last week," Hollister wrote. "We took a hit from a T-34's 85mm gun that should have gone straight through our hull. Instead, it deflected. The crew of 5 men inside this tank owe their lives to your innovation." Such letters arrived periodically throughout the Korean conflict, each describing how the modified armor by then standard on all American tanks had saved lives in combat. Tomaszewski kept these letters in a folder he rarely showed to others, a private testament to the real-world impact of his insight. Mike never sought the spotlight, recalled Robert Mitchell, who had remained friends with Tomaszewski after leaving the Detroit tank arsenal. But those letters meant everything to him. Each one represented lives saved, young men who came home because of something he noticed while welding tank hulls in Detroit. This human impact, rather than technical or institutional recognition, seemed to matter most to Tomaszewski. When interviewed for an internal army publication in 1953, on the 10th anniversary of his innovation, he deflected questions about his own contributions to focus on the ongoing implementation. "Are you still listening to the people who do the work? That's what matters. There are insights on every factory floor and repair shop that could save lives if someone would just pay attention." The interviewer, Captain James Wilson, noted that Tomaszewski seemed uncomfortable with personal recognition, but animated when discussing the broader principle of valuing practical knowledge. He wasn't interested in being celebrated as an individual genius, Wilson wrote. He wanted his case to represent a methodology, not an exception. This methodology continued to influence military technology development throughout the Cold War. When the M48 Patton tank entered development in the early 1950 seconds, its design team included not only engineers and ordnance experts, but also production specialists and combat veterans. The resulting vehicle featured an innovative cast hull with integrated armor slopes derived from Tomaszewski's principles, optimized for both ballistic protection and manufacturing efficiency. General Willard Wyman, who oversaw the M48's development as commander of the Army Field Forces, explicitly referenced this approach in his authorization memorandum. "We are applying the Tomaszewski methodology, integrating practical knowledge from manufacturing and combat experience alongside theoretical ballistics. This combined approach has consistently produced superior results compared to purely engineering-driven design." The Soviet Union, monitoring American military technology developments, recognized the significance of this approach. A classified 1954 report from Soviet military intelligence, obtained after the Cold War through declassified archives, noted, "The Americans have systematized an innovation process that combines scientific research with production-level insights. This methodology, which they attribute to a welder named Tomaszewski, gives them significant advantages in translating theoretical knowledge into practical battlefield effectiveness." The Soviets subsequently attempted to implement similar programs within their own military-industrial complex, though the rigid hierarchical structure of Soviet manufacturing limited their effectiveness compared to the more flexible American approach. By the mid-1950 seconds, as Cold War tensions intensified, the principles Tomaszewski had demonstrated became increasingly crucial to American military technology development. The accelerating pace of technological change demanded closer integration between theoretical research and practical application, exactly the synthesis his case had illustrated. When President Eisenhower warned about the military-industrial complex in his farewell address, he was describing a system that had evolved partly in response to lessons from innovations like Tomaszewski's, a system that connected academic research, industrial production, and military requirements more tightly than ever before. For armor development specifically, the legacy continued through successive generations of tanks. The M60 pattern, introduced in 1959, featured a hull design directly evolved from principles established by Tomaszewski's original welding technique. Its distinctive ballistic shape, with carefully calculated compound angles, represented the full integration of practical and theoretical knowledge that his case had pioneered. Dr. Samuel Livingston, a ballistics expert who worked on the M60's development, acknowledged this lineage in a 1960 technical paper. The armor protection system in current American tanks traces its philosophical origins to a welder who recognized patterns that our theoretical models had missed. Modern design integrates sophisticated computer modeling with the practical insights Tomaszewski's case taught us to value. In 1962, as Tomaszewski prepared for retirement from Allied fabrication, the Army Engineering Corps invited him to Aberdeen Proving Ground for the unveiling of the Practical Innovation Center, a new facility dedicated to evaluating field-developed technical solutions. Without telling him in advance, they revealed that the main building had been named Tomaszewski Hall in recognition of his role in establishing the methodology the center embodied. Standing before the dedication plaque, the normally reserved Tomaszewski appeared momentarily overwhelmed. "I just noticed something that seemed important," he said simply. "All this," he gestured at the facility, "is about making sure others who notice important things get heard too. That's what matters." The ceremony marked one of his last public appearances connected to his wartime innovation. After retirement, he lived quietly in suburban Detroit, occasionally consulting on specialized welding projects, but largely removed from the ongoing development of the methodology he had inspired. When interviewed by local newspapers about his contribution to the war effort, he consistently minimized his own role and emphasized the broader principle. "There's nothing special about me," he told the Detroit Free Press in a rare 1965 interview. "What matters is the lesson. The people doing the actual work often see things others miss. That's true in any factory, any repair shop, any field operation. The trick is creating systems where that knowledge gets heard and used." This principle continued to influence American military technology development through the Vietnam War and beyond. When the M1 Abrams tank began development in the 1970 seconds, its design team explicitly incorporated input from maintenance personnel and production specialists alongside traditional engineers and scientists. The resulting vehicle, which would become the backbone of American armored forces for decades, represented the full maturation of the methodology Tomaszewski had helped establish. Colonel Frank Anderson, who led the early Abrams development team, acknowledged this legacy in a 1975 project memorandum. "We're building on 3 decades of experience integrating practical and theoretical knowledge in armor development, a methodology that traces back to Tomaszewski's welding innovation during World War II. That approach has consistently produced superior results compared to purely top-down design processes." Michael Tomaszewski passed away in 1977 at the age of 78, his obituary noting his wartime contribution, but focusing primarily on his role as a father, grandfather, and respected member of his community. The military acknowledgement of his passing was modest, a letter of condolence from the Secretary of the Army and small ceremonies at Aberdeen and the Detroit Arsenal, reflecting his own preference for avoiding personal recognition. Yet his influence continued to expand even after his death. In the 1980 seconds, as American manufacturing faced increasing global competition, many industries began adopting methodologies that echoed the principles Tomaszewski's case had demonstrated, valuing shop floor knowledge, creating feedback loops between production and design, and recognizing that innovation could flow from practical experience as well as theoretical research. Total quality management and similar approaches that transformed American industry in this period emphasized many of the same principles that the military had been implementing since Tomaszewski's innovation. While few industrial consultants made the historical connection explicit, the parallels were striking to those familiar with both contexts. Dr. William Edwards, who had worked at Aberdeen before becoming a manufacturing consultant, made this connection in a 1985 industry publication. What American manufacturers are rediscovering now the value of production-level knowledge the military learned from a tank welder named Tomaszewski 40 years ago. His case demonstrated that competitive advantage comes not just from better technology, but from better systems for integrating all available knowledge. The collapse of the Soviet Union in 1991 brought access to previously classified Soviet technical documents that revealed how seriously America's Cold War adversary had taken the Tomaszewski methodology. Soviet military planners had identified the American approach to integrating practical and theoretical approach by the relos knowledge as a significant advantage that their own more rigid system struggled to replicate. A 1,967 Soviet analysis, declassified in the 1,990 seconds, concluded, the Americans' systematic incorporation of production-level insights into technical development gives them significant advantages in translating theoretical designs into battlefield effectiveness. Their approach, which began with a welding innovation they call the Tomaszewski technique, creates a more resilient innovation ecosystem than our more centralized model. This post-Cold War revelation reinforced the significance of Tomaszewski's legacy. What had begun as a practical insight about welding angles had evolved into a methodology that influenced not only tank design, but broader approaches to military technology development, a methodology that America's principal adversary had recognized as a meaningful competitive advantage. In 1993, on the 50th anniversary of Tomaszewski's original innovation, the Army Ordnance Corps established the Tomaszewski Award for outstanding practical innovations by non-commissioned officers and civilian employees. The annual award recognized individuals who, like its namesake, identified significant improvements based on hands-on experience rather than formal engineering positions. Sergeant Maria Vasquez, the award's first recipient, had developed a field modification for the M2 Bradley fighting vehicle that improved its cooling system reliability in desert conditions. A practical insight gained through maintenance experience during Operation Desert Storm. In her acceptance speech, she explicitly connected her innovation to Tomaszewski's legacy. Like him, I just noticed something that others had missed because I worked with the equipment every day. The difference is that now the Army has systems in place to listen to people like me. This institutional evolution from the initial resistance Tomaszewski encountered to formal channels specifically designed to capture similar insights represented perhaps the most significant aspect of his legacy. The methodology he had helped establish had become so embedded in American military technology development that it persisted even as memory of his specific contribution faded among newer generations of personnel. By the early 21st century, as digital technology transformed both manufacturing and military operations, the principles Tomaszewski had demonstrated found new applications. The Army's Rapid Equipping Force, established in 2002 during operations in Afghanistan, exemplified this evolution, a dedicated organization tasked with quickly adapting commercial and field-developed technologies to meet immediate battlefield needs. Colonel Bruce Hammond, who commanded the REF during its early operations, explicitly connected its approach to historical precedent. We're applying the Tomaszewski principle in a 21st century context. Just as he identified a crucial armor improvement based on practical welding experience, we're leveraging the practical insights of deployed soldiers to rapidly develop and field new capabilities. When American forces encountered deadly improvised explosive devices in Iraq and Afghanistan, the response reflected this methodology. Rather than relying solely on traditional research and development channels, the military created systems to rapidly evaluate and implement field-developed countermeasures. Solutions often came from maintenance personnel, combat engineers, and other frontline personnel with practical experience, modern equivalents of Tomaszewski noticing something important while welding tank hulls. The Mine-Resistant Ambush-Protected (MRAP) vehicle program, which rapidly fielded specialized vehicles to counter the IED threat, exemplified this approach. Its development incorporated insights from field mechanics and combat personnel alongside traditional engineering expertise, producing vehicles that saved thousands of lives through a development process that valued practical experience. General Raymond Odierno, who commanded forces in Iraq during this period, later reflected on the parallels. The way we approach the IED challenge, integrating practical field insights with technical expertise, has direct connections to how the Army learned to develop armor protection during World War II. Tomaszewski's case established a methodology that continues to save lives 70 years later. In 2015, during a comprehensive renovation of Aberdeen Proving Ground's testing facilities, the Army discovered something remarkable. In a storage room scheduled for demolition, workers found a preserved section of Sherman tank hull, one of the original test sections that Tomaszewski had personally welded in 1943. The artifact, still showing the distinctive weld patterns and angles he had developed, provided a tangible connection to the innovation that had transformed military technology development. The section was carefully restored and installed as the centerpiece of a new exhibit at the U.S. Army Ordnance Museum, with an accompanying display explaining its significance. The exhibit placed Tomaszewski's innovation in broader historical context, tracing how a practical insight from a Detroit factory welder had evolved into a methodology that influenced decades of military technology development. Dr. Jennifer Martinez, the military historian who curated the exhibit, emphasized its contemporary relevance. What makes Tomaszewski's story significant isn't just the lives his specific technique saved, though that alone would be important. It's how his case helped transform our entire approach to innovation, creating systems where practical knowledge from any level can influence technical development. That methodology remains crucial to American military effectiveness today. The methodology continues to evolve in the digital age. Modern programs like the Army Futures Command, established in 2018, incorporate sophisticated digital feedback loops that connect field operators, maintenance personnel, and production specialists with research and development teams. Advanced simulation tools allow practical insights to be rapidly evaluated and integrated into ongoing design processes, creating the synthesis of theoretical and practical knowledge that Tomaszewski's case first demonstrated. Colonel James Harrington, the officer who had supported Tomaszewski's initial innovation, once remarked that its significance extended beyond any specific technical improvement. The welding technique saved lives, which matters immensely. But the more lasting impact was how it changed our thinking about where valuable insights come from. Tomaszewski showed us that critical innovations often emerge from the intersection of theoretical knowledge and practical experience, not exclusively from either alone. This insight that innovation thrives at the intersection of different knowledge domains has proven increasingly relevant in an era of complex, multidisciplinary challenges. The methodology that began with a welder noticing something important about armor angles has evolved into sophisticated approaches for integrating diverse perspectives into technical development across military and civilian contexts. Perhaps the most fitting tribute to Tomaszewski's legacy isn't found in the buildings or awards bearing his name, but in the systems that continue to amplify voices like his, creating pathways for practical insights to influence technical development, regardless of their origin. In that sense, every field modification that saves lives, every production-level innovation that improves effectiveness, and every practical insight that shapes design carries forward the legacy that began when a Detroit welder noticed something important about how metal behaves under impact. The story of Michael Tomaszewski reminds us that innovation often comes from unexpected sources, that crucial insights frequently emerge not from formal research programs, but from the accumulated wisdom of those with hands-on experience. His legacy isn't just about a specific welding technique that saved lives in World War II, but about the broader principle that innovation thrives when we value knowledge from all sources and create systems where practical wisdom can influence technical development. As one tank commander who survived a direct hit in Italy wrote to Tomaszewski in 1944, "You saved my life with your crazy welding angle." But the real miracle is that someone listened to you in the first place. If your story teaches the brass to listen to the men who actually do the work, that might save even more lives in the long run. 70 years later, that insight remains as relevant as ever, a testament to how a single welder's observation, properly valued and systematically implemented, can influence not just specific technologies, but our entire approach to innovation and problem-solving in complex systems. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.